So good morning. Today we are going to see part 2 of cam and followers. We are going to discuss about uniform acceleration and retardation, simple harmonic motion and cycloidal motion of the followers. I am Vijay Lakshmi, Assistant Professor in Mechanical Engineering, Thandai Periyar Government Institute of Technology, Vellore. So as discussed earlier, the follower may exhibit any type of the motion. We were discussing we had four types of motion: uniform velocity, uniform acceleration and retardation, simple harmonic motion and cycloidal motion. In today's class, we will be discussing about the three types other than uniform velocity, which was discussed in the previous lecture. So the displacement, velocity and acceleration diagram when the follower moves with uniform acceleration and retardation. So here in this diagram, you can see the displacement diagram. So how to draw the displacement diagram? So for all, as already seen, for the displacement diagram, we have the theta along the x-axis and the stroke or the lift of the follower along the y-axis. As usual, we divide the outstroke into 8 equal parts. So you can see we are dividing it into 8 equal parts. Now take the center line, divide the center line also into 8 equal parts. So A, B, C, D, E, F, G, H. And again you can see 8 equal parts. Now join the center point and the two corners. So join AH passing through D. So the lower half you join with the corner A. The points in the above half you join with J. You can also name these points as 1, 2, 3, 4, 5, 6, 7, 8. So the line from A will meet the line. Already you have the A point, that is 0 point. So the line from A will meet the line from 1. That will give the first point. The line from B will meet the line from 2, second point. From C will meet the third line from 3, third point. So it is better if you are numbering it as 1, 2, 3, 4, 5, 6, 7, 8. So from 1 and this one, 1. From 2 and the line from 2 meets, you get another point. From 3 and the line from 3 meets, you get another point. And similarly, the line from 5 and this 5 will meet 6 and this 6, 7 and 7. So if you join all these points by a smooth curve, you get the displacement diagram of the cam. And this is 12, 12. And the same procedure you have to repeat for the return stroke. The thing is, for the return stroke, you have to take the corners from right to from the topmost corner to the bottommost corner, whereas for the rise we took from the bottommost corner to the topmost. So join the line, similarly divide it into 8 equal parts. Divide the, so you have to join the topmost corner with the bottommost corner of the written stroke. And similarly you divide the center line into 8 equal parts. The top half with the topmost corner and the bottom half, the points in the bottom half with the bottommost corner. The same procedure should be repeated. And it is also preferable if you are, so the line from 1, if you are numbering it in the reverse, so 1 2 3 4 5 6 7 8 0, so 0 1 2 3 4 5 6 7, so you join all these corresponding lines. So this is 1, so you just assume it is the opposite ones. You can either number this or here you can change the order of numbering. 8 7 6 5 4, so that you can get the corresponding numbers. So once you got the point, you join those by using a smooth curve. So this is the displacement diagram. So you can see the velocity diagram. So in the velocity diagram, the maximum velocity is at the middle point, and when the displacement is maximum, velocity becomes 0. So here you have no change in the displacement, so velocity is 0, and here velocity decreases, so the maximum velocity in the negative direction will be again at the middle, which is the average velocity, and then the end, the velocity is 0. Since this is a uniform acceleration and retardation, you can see the acceleration is uniform. At the center it reaches 0, goes to the negative maximum, constant, becomes 0. When velocity is 0, acceleration is 0. Along the negative side again you have the constant acceleration and you have the positive acceleration. Since the maximum velocity of the follower, so you can see that the mean velocity is equal to minimum plus maximum divided by 2. So minimum is 0 and the maximum velocity is Vmax. So you can see that the maximum velocity is nothing but twice that of the mean velocity. Therefore, the maximum velocity of the follower during outstroke V0 is equal to displacement by time. So displacement by time is the mean velocity. Since that is equal to 2 times the mean velocity, you have 2s by t naught. We know that omega is equal to theta by t. So t can also be written as omega by theta naught. So v naught is equal to 2 omega s by theta naught. Similarly, the maximum velocity of the follower during the return stroke is equal to v return is equal to 2 omega s by theta r. Next, we will find out what is the maximum acceleration of the follower during outstroke. So we know that acceleration is equal to two times the mean acceleration. So 2 into v naught by t, or this can 2 into v naught by t, where v naught is equal to 2s omega by theta naught. So acceleration becomes 2 into 2 omega s by theta naught t dot, or theta o t o. So it's nothing but 4 omega square s by theta o square, where theta is the angle covered during the outstroke. Similarly, the maximum acceleration of the follower during the return stroke is, so instead of theta outstroke, we substitute theta outstroke for theta return. So if you substitute the angle, you can see AR is equal to 4 omega square s by theta r square. So this gives the maximum acceleration of the follower during the return stroke. So with this, we'll wind up this part of part 2, uniform acceleration and retardation. So to summarize, we can see when the follower moves with the uniform acceleration and retardation, the velocity is maximum at the mid displacement. Similarly, during the return stroke, velocity is maximum at the mid displacement. When the displacement is maximum, velocity is 0. Since it moves with uniform acceleration, so it reaches the velocity, maintains the same acceleration, then it dips to the negative, maintains the same acceleration, and reaches 0. And then we derive the expression for maximum velocity of the follower during outstroke and return stroke, and maximum acceleration of the follower during outstroke and return stroke. So the next rest part of the remaining 3 types of follower motion we will discuss in the next class.